Thank you, Monica, for the introduction. Hello, everyone. My name again is Tanika. I am a data scientist. I work primarily on machine learning ops projects in the US for the Navy, but I also really enjoy doing business intelligence based solutions and really focus on data science as a service, meaning I build models, my team builds models for the organization to come in and basically like pick it up like they're in the grocery store and take it back to their organization. Outside of work, though, I really enjoy just finding a passion with connecting with people and enjoying how people can get connected to like opportunities like data science for all and teaching data science to different individuals in the community. One of the biggest passions I do have is like, how do you visualize data so that it can tell the story that the business needs to know? So that's something that I really enjoy doing. And I think it's one of the areas that I'll always take with me. Today, you are going to learn a little bit more about regression and how to look at residuals and outliers to really fit your model to a line. I don't know if you all have ever watched like Stats Quest videos, but those are like my favorite videos to watch when I'm looking at any statistical problems, because they really do help us understand what's happening with the data. And they really help me understand and refresh my brain on what my team is doing as well. So let's open up the case. Let me go ahead and share my screen. All right. Okay. I hope you all can see my screen. I think it is sharing according to Zoom. Good morning. Good morning. All right. So in the case today, we are going to talk about how much should a property be worth, specifically in Milwaukee, Wisconsin. I don't know anyone that lives in Wisconsin, but I feel like a lot of the properties in Wisconsin could vary because there's a lot of land there and then there's city. So we're going to talk about how some models could be extremely useful for an organization and some models can't. My team works on different models and we're really looking at like what is the precision of this model and the accuracy of this model before we give it back to the business. The reason is if we give the model to the business, and it really does not help them solve their problem, then that model they would say is trash. So we want to make sure that we are building very good, useful, and acceptable models. And one way of doing that is to really understand what is the precision and accuracy, what are the outliers, and how can we really revisit those residuals. So your case starts with this quote from a famous statistician, George E.P. Fox, which says that all models are wrong, but some models are useful, which is super funny because there are a lot of models that you can tinker with until it becomes useful. All of the models start wrong, but then you tinker, and then it becomes some type of useful. So what he's saying is that our world typically behaves in a way that all of the variables are completely out of our control. Let's say I decide to go get my car fixed. I'm going to get my car fixed. I drive a regular Honda Accord, and I know when I go get my car fixed, they could easily probably realize what's happening with my car. Versus when my friend gets her car fixed, who has a Mercedes G-Wagon. It's a very popular car, but it's a Mercedes. She has to go get it her car put on, or a truck put on a machine, because there could be so many things wrong with it, that you can't isolate it to just one thing. Whereas a Honda Accord, you pretty much know, because a lot of people have worked on those cars. And a lot of people know when something happens, they can predict what the issue or the root cause of that issue is. Whereas her car, she has to go, whew, I did not know that. Here, a G-Class Mercedes is 4 or 5 Honda Accords. So it is extremely expensive. I would not have one. But it's one of those vehicles that you just don't know what's going on, and you don't know what's happening, unless you go to a specific dealership, like a Mercedes dealership, and then you get the car tested with the diagnostic machine, and they figure out what the root cause of it is. So what we're trying to do in this case is essentially mitigate what that issue is by improving our understanding of what the errors could be in our model. What this helps us do is make this model more useful. So when something is happening, so when a car is breaking down, we are able to leverage what factors. Is it the engine? Is it the oil tank? Is it the alternator? What are the different factors contributing to the issues in this vehicle? And then we can predict a solution, similar to when you go to the doctor as well. And they say, okay, well, are you sick? Are you coughing? Are you wheezing? Are your eyes watery? The more factors we have, we're trying to really understand and predict how useful these factors are in the outcome. Maybe I have the flu. Maybe it's COVID. I don't know. But a model is tinkered with until it is found useful. So the goal of this case is to really learn how we conduct proper analysis of errors in our model, which are residuals, in a linear regression model, and understand how this model could be useful to make improvements. All right. Yes, Claudia. So funny, with the new chip shortage that happened because of COVID, all of the used cars are so expensive. Like, an older Honda Accord is now just as expensive as a brand new car, because they still have those chips that people can't get to because of COVID, because of the shortage. So it is not a good time to buy cars. All right, so let's get into the case. So first, what we're going to do is load our packages. If you haven't already done so, go ahead and load your packages. And then we're going to go through the context of the case. Feel free to read through it while I explain it. Andres, yes, you have to, if you want to work at data science companies, specifically on a data science team, you definitely need to know the stats models. They use them all the time. But some companies say they're data science and all they do is run SQL queries. So it really depends. All right. So for this case today, what you're going to do is evaluate the real estate market. And we know that if you are buying a house right now, it is probably extremely high. But we are going to evaluate the real estate market at a point in time. And what we do know is that buying a house is very stressful process for the buyer, stressful process for the seller. And it creates, are you buying the right thing? Are you sure this is the investment you want to make? I'm not sure if this is the house that I want to live in forever. It creates so many different emotions, and it's a very psychological process that can create irrational fears. So we really want to make sure that the price we're paying is based on or anchored to the negotiation. So you want to remember that as a buyer in this marketplace, that initial number usually sets the standard of which the seller could go up or down. For example, when I purchased my house, the house had a set price and I negotiated incentives and a little bit lower, but the price on the house I knew would not go too far low because similar homes sold for right at that price or lower. So if you are building homes and you frequently also buy homes, it is very useful to get a fair estimate of the market and the property that you are looking to buy before seeing that asking price. So what that means is when you are looking to purchase a home, what you want to do is understand based on the square footage, the number of bedrooms, the number of bathrooms, the location of the home, what is the price that you should pay. So when you are looking at this, there are models that are developed that keep you super informed on what the price is for the houses in the markets right now. One of the areas is of using models as well. Like if you work for a real estate company, they always use data science to make sure that their homes are not undervalued as well. They also have apps that let you know if a home is undervalued. Maybe you want to send an alert to someone. And you can also estimate the value of a home based upon how many homes recently sold for that price. That's another thing that you could do. Okay, so let's go into all right, so what we're going to do today in this case, you are going to build a model to predict the property prices in the city of Milwaukee, Wisconsin, in the US. And the data set that you're going to use has the property sales, which have both commercial properties and residential properties. So you have business properties in the same data set as residential properties, which already tells me that that could be problematic. And the data goes from 2002 to 2018. So we're going to take out the COVID effect of everything, but it only goes up to 2018. So we're going to use linear regression, and we're going to fit a line through the data. But it sounds very simple. The baseline points are when we fit a line to the data, the coefficients on that data can be easily interpreted. It's also very straightforward to understand. If you remember y equals mx plus b in high school, that is essentially what we're talking about. But there are not as simple. Y equals mx plus b does not always work. So in this case, the structure of the case will be, we're going to explore the data so that we know and can pick up on some initial patterns. Then we're going to analyze the residuals in the data, which are, residuals are the difference between the actuals versus the estimates. And then we use that to diagnose an initial model. So once we do that, we're going to do some various transformations. We're basically tinkering with the model to deal with those outliers and any problems with the residuals. And then finally, we'll look at how to deal with it even further. Okay. Daniel, in this case, we are not adjusting for inflation right now. We should be adjusting for inflation in 2022, but not right now. Okay, so first what I would like you to do is explore the data. This is your what I call the data dictionary. And what we're going to do is run the read function for this CSV. First and foremost, does anyone see anything odd or out of place with the features? William, yes. So when you are working with features, you want to make sure that you are not utilizing things that could be seen as categorical variables, like a neighborhood. What value do you get calculating the average for a neighborhood when these values, the neighborhood is just saying one is a neighborhood in Milwaukee. Stories is the number of levels in a house. So when we talk about stories, you talk about how many levels your house has. Do you have stairs that go upstairs and downstairs? So if most homes are 1 or 2 stories. All right. So looking at the data set, see if there is anything else that we should be exploring in this data set. What happens? Oh, let's look. Well, remember when you do the head of the data, you only get the first 5 rows of data. If you want more data, you can put in this and it will give you more data. But we're just looking at the header. There are a lot of nulls. Yes. So what we're going to do now is think about what do we need to do with null values? So first and foremost, let's look at the nulls, right? If I run this function, I realize that there are a lot of null values. Yeah, I can zoom in again. You're welcome. Okay, so there are a lot of null values, and sometimes when you have missing numbers, when you are running functions like average or minimum or maximum, this could really affect your calculations. When people have null values, they tend to enter them sometimes as zero, and that can really mess up how we calculate. So when we look, for example, at lot size, going back up, this is lot size, right? If there was a null value entered here, that would really affect how we calculated our model, because that is a key feature in our data set. So what we're going to do before we proceed is remove those rows with zeros in the following fields. We want to remove anything with zeros in year built, because a house has to have been built in some year. We want to remove anything with a zero in square footage, lot size, and sales price. And then we're going to plot it so you can see what that looks like. Thank you, Laura. All right, let me just check in the chat. All right, so now that we have removed those with zeros, what we're going to do is just quickly run a numpy log function on lot size so that we can create a histogram. And now we'll see, can someone tell me what type of distribution? So when you have lot size, when you do a logarithmic function, it will create a negative value. So you want to turn that negative value to a positive value. So what we're doing is running the numpy log function, and we're running that function on lot size, which will produce some negative value. But we need to turn that negative value into a positive, so we add 1. And we want 100 different bins in our histogram. So that is what that parameter is for. It's skewed to the right. Yeah, that 0 is really putting us out there. Very out of place. So we want to also make sure that we are removing any other confounding factors before we really create our model, because we want to focus on the residential properties only. So when we're thinking about the home prices, residential properties are what we're really focusing on, not commercial. And the commercial properties would skew our data completely, because the commercial prices are completely different than residential's. They're also highly subject to any economic or market conditions that residential prices aren't. Someone mentioned the inflation in the 2000s. What did that do to residential home versus commercial homes? We don't know. So we're going to just go ahead and remove any of those categories. And this is how we do that. We're creating a function. And let's walk through this function. So what we're first going to do is create a function called remove any unused categories. All right. So for every category name in our data set, I like to read my code out like it's a book. Otherwise, I don't understand it. So for every category name in the data set, any column that equals the category name, if the type of data from this data set, that's what this is saying, Pandas API. If the type of data is a categorical data type, from that category name in the data set, we're going to remove any unused categories and then return that data. William, we use log because there were values entered as 0. So we wanted to make sure that there's no erroneous 0 values in the values did not skew the distribution. Okay, I will read the code again. All right, so we are defining or creating a function called remove unused categories. We're using this data set that we defined earlier. So for every category name in the data set, we're going to do the following. For a column with category name, if this is the data, if that data type is categorical, we are going to take the category name and remove it. So what this is going to do is check each row in the data, each column in the data, and it is going to go through each column and keep going and keep going and keep going. So when we look at the categories that we defined earlier, the categories were property type, district, exterior wall, neighborhood, and style. Correct. It is looping on each of these. So it's going to check, is property type categorical? Yes. Okay. It is categorical. Yes. Now it is going to do the function that it says removed unused categories. So if this category is unused, it will remove it. So going back to our function, if it is categorical, which it is now going to remove it from the data set and then return the data. And then now what we're going to do is clean that data. An API is a way to access data. So let's say you want to access data from a particular website. That is typically what an API is. But in this instance, what we're using the API for, this function, is to check whether an array or data type is of the string data of the string data type. So we made these columns categorical. You can also do date time. So basically, this is to check the data type. And you can say, is it a date time? Is it an integer? Is it a float? It's basically checking the data type. It's of that set of data. What is the criteria to define if a category is not used? Okay, so let's go to the data set. In the, let's go back to, in the function, what we're doing is running only residential on the property type. So what this is also doing is when we run this function, we want to create a coefficient. So if you remember, like y equals mx plus b, you need a coefficient for each category in that column. So if we have multiple categories, we're going to pollute basically the results of the data. So when we set our clean function, we are only setting that function to be residential. Oh, the chat is moving. Let me check. So we are running this function because when you're working with data sets, so this is what someone also shared in the chat. So when we are working with data sets, so if I have a category, for example, residential versus neighborhood, anything that is not used, I don't want to include it in the data set. So in this example, this is A, C, B, C, D, A, B, C, D. But we are only looking at A and C. I'm going through the chat. The other reason that you also want to make sure that you are removing any unused categories is because when you're running your data set, you can't, I talked about earlier, you don't want to compare commercial prices with residential prices. So we want to delineate the difference between a commercial model a model that we're running on commercial homes and then residential homes. Yes, we are losing the commercial homes, but we are only running this model for residential purposes. We don't want to say, for example, Tanika wants to go buy a home, but her home is 1,000 square feet, and the commercial property up the street is also 1,000 square feet. So that property is $200,000 more. Should she also pay $200,000 more? No, because it is a commercial property and not a residential property, it costs more. So when we're running our models, we want to make sure that we are using the right one-to-one comparison. It will also create outliers in our model when we do use two different categorical comparisons. So comparing residential from commercial. Okay. I'm just trying to go through the chat. Some people have already answered. Okay. Perfect. All right, someone summarized it. So now going into the clean function or the clean statement. So now we're cleaning the data to make sure that the data, we are eliminating any outliers or anomalies in our data. So we want to make sure that the sales price on the homes are over zero. If you have a sales price at zero, at zero or below zero, that's probably an error. That erroneous data could lead to errors within our model. You also want to make sure the home is built over after the 1800s and that the data doesn't have a negative or zero square footage. Same thing with lot size. And then we are going to say residential for the property type. And now what we do is we have this function, which is the clean data. So we've ran this NumPy filter to filter out any data that doesn't fit within these, what we've specified. And now we're going to say all of the data that is clean, give me a copy of that data and run this function, remove unused categories, on the clean data. And now show me the top 5 records. Well, your reasons, Maritza, that you would want to remove data is, what are your requirements? So I would remove data to understand what are my requirements for the model. In this instance, we are running it on residential data. You also want to relook at your data dictionary. What does the data dictionary say? And for the context of this case, this is their data dictionary. What are the things that you know? For example, I know that a house cannot be negative stories. I know that a house cannot be 0 stories. We typically don't want to look at houses that were built before the 1800s. That's just a very normalized piece of information. Most homes were built after 1800s. If they were built before the 1800s, they were built with materials that are unsustainable. we also looked at neighborhood, which was an integer. So typically a neighborhood has a name. So that's why we updated the neighborhood earlier. So basically, you're going to look at your data set and the requirements of the case to really understand what data you need to remove, what data you need to understand. Typically, what I would do is run some type of model, regression model, to really understand what features are available in the data set. So in this data set, there's also 5 different property types. So you can also run the data set and understand, oh, someone actually just said this. You can also run a regression on the data set to really understand, are these features valuable or are they skewing the data? You will really analyze their p-values. All right. Perfect. Okay. So now what we are doing is looking at the data set now. So what we have now is just residential properties. Everything is built after the 1800s. There are no stories that equal 0 and no square feet that equal 0 as well. Weimar, yes, that's exactly what I would normally do. Is I would look at the features, I would check out the p-value and really understand what's happening. But first, what I normally do is clean the data set. So I would clean the data set first and then run that. But my business requirements are just for residential. So that's another instance where myself, I am very exploratory. I would probably run it, but my business requirements state that it should be residential. So I would always eliminate that. You can have a house without a bathroom. I don't know if someone wanted to buy a house without a bathroom, but yes, you could have a house without a bathroom. All right. All right. So yes, that is still a concern that those are bedrooms, bathrooms. So this is a unit. One of the things you'll also notice is the units. One of a home can be labeled. So if you really look at your data again, where you see style, you also want to really explore your data. So the one of the things that I really like to do is I take about an hour or so to really understand the data, especially if it's a data set that I have never seen before, or it is a business use case that I have never worked with. Like I've never worked with real estate clients. So it might take me a little bit of tinkering, running different functions, filtering the data, understanding the data. Like when you all said a room, sorry, there's this is full bath, this is half bath, this is bedrooms, this is units. Something with 0 bedrooms, but 6 units, that would concern me. So when I look at it, it is a room or a rooming house, which means they have they may have where there is ideally 1 bathroom at minimum and a bunch of rooms separated in that house. But it doesn't have any bathrooms, which is concerning. So the other area I would think is like, this is really odd. Typically it's also called like a boarding house or a multi-tenant house. That's what rooming house means. So yes, I would want to really understand that more. Okay, let's go to the exercise. All right, so first we want to visualize what is happening with the data. So you ran logarithmic functions, I was told in your previous courses. And there are some different variables. So we're going to write some code. I'm going to give you 10 minutes. So I'm going to give you 10 minutes to, or I think it's 10 minutes. Let me see. Yeah. So it says 15 minutes to write this exercise. Yes, that is askew. That's so cool that Google makes it skewed when you search that. I have never thought about that. Okay. So I just saw your screenshot, William. Looks like it says the parameter is deprecated, but the return function actually is not. Boolean, the in place for Boolean default false. This happens all the time. Okay, so here is one potential solution that you could have. And this solution is checking the logarithmic function for each feature: units, district, year built, square footage, bedrooms, and sales date. So what do you notice about these plots? Oops. Look at these questions. So from these plots, would you say that properties built in the last 10 years are more valuable? Would you say that dividing a single unit property into smaller units would make it more valuable? Are many of the most valuable properties in districts 3 and 14? Does having more bedrooms make a property less valuable? Let's go through this. Okay. So for these properties, some of the most valuable properties are actually, let me go zoom in for you. Some of the most valuable properties are newer, and some of the least valuable properties are older. So there is no trend there for A, so that is false. For B, while it is true that when you divide a property into separate units, it can be more valuable, but you can't tell in these plots because the property itself is still seen as one property. What it also shows in these plots is that if a property has been divided, it's actually showing up as less valuable than those single unit properties. So it could be reasonable to say that residents in this area have a preference for living in single family homes instead of multifamily properties. There's a key difference here in what you see in your violin plot. So just want you to explore. When you are looking at the price per square footage, when it is the top of this plot, it's actually higher. And then, so at the 1 unit and the 3 unit is next. So while when we look at the properties that are the most valuable in the district, so we look at District 3, the next one is 14. Those are the properties that have the top peak for their violin. So they have one of the most valuable properties. And then the last one asks if any of the properties with more bedrooms make it less valuable. I would think no immediately, but you can also look at the peak here. You can suspect that the properties with many bedrooms are actually larger and they do have multiple units, but it confounds the trend seen here. Okay, we're gonna go to exercise 2 really quick. And we are going to look at some of how would you potentially fit a multiple linear regression model on the sales price of a home against the district, the number of units, and the finished square footage. So these are some of the features that we looked at earlier in the previous example, and we want to do a multiple linear regression model on sales price against the district where the home is, the number of units the home has, and the square footage of the home. And then we want to know which districts does this model see as having the most valuable properties? You want to make sure you pay attention to your coefficients and how you interpret those coefficients. So, going back to this, I just pasted the code in the chat so we can evaluate our model. When we look at our model, we want to pay attention to the coefficients and the p-values. So when we look at these values, can someone tell me which district already has one of the highest coefficients? Perfect. District 3. So District 3 has one of the highest coefficients. Is this significant? What does the p-value tell you? Perfect. So basically, your p-value is telling you that it is statistically significant. It has a 0. What about the p-value that you see for District 8? What's happening there? It's greater than 0.05. It's not significant. So we might need to reject, we might need to really evaluate what's going on with this value. Basically, the smaller your p-value, the stronger that the evidence is to reject the hypothesis. But looking at this case, so what we're seeing here is also that there could potentially be, let's go back to district 3 points. Okay, so I want to go back to the districts. So the highest district, a lot of people put 3, and then there's 8. So the higher coefficient is actually 14, not 3. And then let's go back. Keep exploring all of your data set before you come up with the answer. Okay. All right, so what we also just want to note is that our standard errors assume that there is a covariance matrix of the errors, and it is correctly specified. There could potentially be strong multicollinearity as well. So what that means, what that means is, so one, this model, district 3 and 14 have the most valuable properties. District 14 is the highest. District 3 is the second highest. But when we look at exercise 1, we also saw that district 3 and 14 had the highest peak on the violin plot. We also saw that the coefficients for district 12 and 8, so looking at 12 had a p-value of 0.23, 8 had a p-value of 0.86. They are not statistically significant, or there's no statistical significant difference between the prices of those properties of districts 1 and 8 as well. And districts 1 and 12, when you look at actually the number of units of those properties and the square footage, there's really a lot more to consider. Sorry, I just heard something fall in my house. Okay. Going back to the next problem. So what we're going to do next is look at how do we evaluate our residuals. Let me see. When we're looking at linear regression, so one of the biggest areas that we want to evaluate is how are we fitting the line to the data? When you are looking at linear regression, there's a lot that could be misinterpreted. It could be evaluated incorrectly. Residual analysis is one way to diagnose any issues with your model that could potentially affect the linear regression of that model. And when we think about residuals, they are the difference between Y and Y hat. So it's the difference between what you observe versus what you fitted. And when you look at it in a line, it is essentially, let me see if I can draw. So when you look at it in a line, it's this. If this is your line, you are looking at it is asking you what is the difference between this line and this dot, right? So this analysis basically lets you test any of your assumptions that use linear regression. Linear regression is a very highly used model in all industries, but it only really works best when the residuals are normally distributed. you have to come across residuals that are normally distributed. And you may hear people say, oh, well, linear regression assumes that data is normally distributed, but actually it's not. When I have data scientists on my team say that, it's a red flag for me. But it is a very useful and powerful tool, even if it is not normally distributed. And the data, when it deviates from that assumption of being normally distributed, what we tend to say is when that distribution has a fat tail, it's a problem for linear regression because it points to the tails that are further away from their fitted values. What happens then is that it disproportionately affects the coefficients and the predictions. So with one point on your plot having issues, it could be a misplaced decimal, it could be how we cleaned our data, it could be how the data was entered into a spreadsheet, maybe someone miswrote it. It could cause a lot of issues on your model. So you have to have a lot of leverage on the model. What we're going to do now is compare our observations from our model against the fitted values using the model len, which is a function that allows you to do just that. So what we're going to do is run this model. And let me go back. So when we run this model, it should look, just gonna, I think it was posted and posed an announcement. I'm gonna post it in the chat. You're gonna run these 2 lines of code. And what you're doing is saying my residuals equals the data, the clean data that we already ran, dot sales price, which is the fitted values. So the column sales price minus the fitted value. We want to see how close the sales price is to the fitted value. So you're going to run the column sales price minus the fitted value. And you're going to see the differences between the residuals and are they all 0? And you can run the numpy function all close to see if it returns true. Yeah. Okay. We're going to apply very simple. We're going to apply what we just learned into a plot. So what we're going to do is plot a histogram and a QQ plot of the residuals. So what that means is, let me go back. Okay. The QQ plot is we're going to plot the quantiles of the first data set against the quantiles of the second data set. So in this example, what we're going to do is compare the residuals histogram to see if it's normally distributed. And we're going to use the parameter density equals true. I'm sorry, the argument density equals true, so that both histograms are on the same scale as the normal distribution. And then we're going to add this code to the bottom. I'm going to put this in the chat. Okay, reading out the code, we're going to plot a histogram. We want to use the residuals in our data set. We want to compare it to normal distribution. So we're going to say density equals true. Oh, Eileen. Oh, Maria explained it. Okay, cool. Let me just go back really quick up. So you are comparing, when you look at residuals, your observed value, which is sales price, minus your fitted value. So Maria is correct. Okay, going back here. So we are plotting a histogram with the residuals. We want it to be compared to normal distribution, and we're going to use 100 bins. We're going to label the bottom residuals. So this section is going to be labeled residual, which is red. And then we're going to plot normal distribution on the same plot so that we can compare it. So what we're doing is saying, in this linear space, we want the minimum value of the residuals, the maximum value of the residuals, and we want it to have 1,000. So we're then going to plot this in normal distribution, and it's going to be in blue. And then we're also going to plot our outliers. We're going to take the absolute value of our residuals, which are greater than 4 the square root of the scale of this plot, which is here. What we're doing is, and those are going to be in green. And what you'll see in this plot is essentially, first and foremost, your plot is, oops, let me see, in blue. So you'll notice that your peak here is actually higher than the normal distribution. This is also very narrow. This is also very narrow, smaller than normal distribution. You'll also see that there are outliers, less on the left, but more on the right, on both sides of the histogram and on normal distribution. And your residuals are not symmetrical, meaning there are some particularly large outliers, again, on the right side. So we're literally visually diagnosing this, but what we see here is that this data set is positively skewed and there's high kurtosis, which is an issue. When you're looking at your data, the skewness of that data, which is the shape of your probability, means that we really need to investigate what's happening, because different data scientists could interpret this differently or interpret our model differently. So we also do a QQ plot, which also shows non-linearity and more like a warning sign. Okay, let me scroll down, clear my visuals. Okay, so here what we notice is that there is some levels of heteroscedasticity. So we see that with our plot, oops, let me close this out. With our plot right now, you'll see there is an area of the plot that, this is the line. I'm actually going to draw the line so you can actually see it a little bit better. But that's the line of the plot. And what's happening is the residuals have a variance from that line. So remember, there's a small variance, it's not on each side. There's a high variance on the top and a small variance on the bottom. This is an issue because with the data points having a larger variance, it starts to really go into heteroscedasticity and homoscedasticity, which is what we usually want to see in the data, which mean that the residuals have a similar variance across all subsets of the data. But when the data points are really, so what's happening essentially is homoscedasticity, it has the same scatter. So with homoscedasticity, the points are around the same distance from the line. And in heteroscedasticity, meaning the points vary very widely from the regression line. So you'll see on the top, there is a larger variance than there is on the bottom. Okay, so we should investigate that further. Clear my visuals again. Going back to the chat. So what we're going to look at now is actually standard deviation. So that variance that we were just talking about, when I talked about the hetero and the homoscedasticity, when you view a chart, you can easily see the distance from the points to the line, and you can determine if it's homoscedasticity or hetero. But the variance is what counts because it's what you use in calculations. So the variance is essentially your standard deviation squared. You usually use homoscedasticity as a condition where the standard deviation is equal to all points. So typically your variance is going to be greater than 0. Let's look at the standard deviation here. So you have a home, a couple homes, 2 homes in Milwaukee, house 1 and house 2. You want to know, you have a sales price, and you want to know house 1 has 60,000, is a sales price of $60,000. House 2 is a sales price of $7 million. You know that the final selling prices, although these are the listed prices, your final sales price could be different. But it will depend on different factors in your model. So in the end, your actual sales price can have some standard, there can be a deviation from the list price. So maybe it sells for 60,000, maybe it sells for 61,000, maybe it sells for 59,000. Same thing with the $7 million home. What we're wanting to understand is when we think about standard deviation, which deviation do you think would be larger? The $60,000 home or the $7 million home? And this is more theoretical. You're not writing any functions around it. Okay, why do we think the $7 million home would be a larger standard deviation? Using the plot. I like it. I like it. So we're going to validate this in a second, but yes. So the spread of the data again was higher was higher. So we should expect that the $7 million home's standard deviation is larger than a $60,000 home standard deviation. So this just means essentially if I had $60,000, I'm looking at a home that's $60,000, I might not look at a home that's $65,000, $70,000. I may not have enough income to buy a home that could go a bit higher. In the US right now, the housing market is crazy because some people are coming in and they're making a home that's $60,000. They say, well, I'll pay 100. You are completely eliminating anyone else who would even consider that home because they don't have the same income. So a person that's buying a $60,000 home is not typically going to spend $10,000 to $20,000 over budget. But a person who's buying a $7 million home probably has flexibility in their budget. One, yes, there is word on the street is Wall Street is buying a lot of these homes. So I'm sure they have a lot of money to just throw out there. But those individuals buying the $7 million home maybe have $500,000 to put onto the home value. Not everyone has that. Okay. So what we're going to do is validate what we found by really drawing a scatter plot of the residuals. So what I want you to do is create a scatter plot of the residuals against the square footage to see if they're homeoscedastic or heteroscedastic. And in order for us to see this variance, you might want to do subplots. I'm sorry, not subplots. You might want to subdivide the data into the square footage into 4 bins. And you might want two separate plots, but it will help. So let's see what that looks like. Here's one possible answer. Okay, so I just gave you the code if you like it, so you can see the plots in this case. And I'll give everyone about 2 more minutes just in case they still want to try their own code. Okay, so I just wanted to show you all these fun and fancy charts. So violin chart, again, this is your kind of max, the min. So this one is the square footage. We're looking at the square footage, the residuals on each. So for 4,500 square feet, this one has higher and the highest and the lowest residuals. We can also see that when we look here and going down. Oops. So what we notice is pay attention to how big these get. So look at this is 500 square feet. Every time the property size increases, the residual gets bigger. The difference between 3,500 and 4,500 isn't as big as the difference between 2,500 and 3,500, but there's heteroscedasticity in our data because this difference is wide. That's how I like to look at it. When I look at this tells me it's heteroscedasticity because my points they get wider. And homoscedasticity is hard to demonstrate because basically you have to say that none of your variables exhibit heteroscedasticity. Basically, you're using your own thoughts and intuition to look for heteroscedasticity. So it is very easy to see here that smaller homes have a more predictable sales price than larger homes. A larger home could have an extreme, look at the median here. The difference from the median, oh my gosh. So these larger homes, the sales price is very unpredictable. You can also plot this in different ways too. Thank you, Haya. Okay, so let me clear. I want to show you one more way to do this. And you can put these two plots on top of each other. I'll give you the code, but I just want to show you this. So if you want to put your plots on top of each other, this is one way to showcase what your plot could look like if you wanted to see the violin plots. Another data set that exhibits homoscedasticity. What would be another one? Let me think. I have to think about that. Let's see. Another one. Oh, I guess it's still home related, but in construction, the amount of, and I only know this because I had my home built, but the amount of material, the more square footage you have, that one also shows the same thing. I'm trying to think of another one. I'll have to think about that one. What other data sets? I'll think about it. Okay. What was I saying? Okay, so what you see is a larger variance in your data sets. When we also think about how much money people spend, that's probably another data set that will look probably similar to this. When you have more money, you spend it. Some people spend it frivolously, some people spend it on luxury, some people buy art. I think that plot probably would look similar to this plot, because the more money you have, the more you would spend. So I think that one might be a good example. But outside of that, okay. And let me go back. So with these issues, with these residuals, again, you still have the same issues going on here. Excuse me. With this and the variance, you still have these issues. So when these residuals are extremely problematic, you have to figure out what you're going to do about them. So a solution is to basically use what you learned in previous lessons and do that transformation, the logarithmic transformation on sales price. And what you're doing is assuming that sales price is proportional to the square footage of the property. So we know that sales price increase as the property increase is probably highly correlated. So what we're going to do is take the logarithm of square footage as a predictor in this model. So essentially, I'm saying if I enter in the square footage, I can predict how much the home price is going to be based on my model. So when we look at this, model, oh, let me go back. I think the one that is harder to predict is homoscedasticity. It is very hard to demonstrate it because you have to show that none of the variables exhibit heteroscedasticity. So you have to investigate the variables for heteroscedasticity first and basically like really evaluate all the variables in your equation. So going back to the transformation of the residuals. So essentially, we're taking the logarithm of the square footage here. And what we're doing is, this is the dependent variable, is sales price. And the logarithm of the square footage is our predictor variable. So we are looking at sales price as our dependent variable. And then we are looking at the data set. Anything out of place here? Always check your p-values. Which one might we have issues with? Diego, yes. So when you're in banking, banking, they look at how much people spend on your credit cards, especially credit card companies. So they highly correlate. If you make more income, you're likely to spend more. So we should give you a higher credit limit so you can keep on spending, which means you will start to owe us more interest. And so that's why I was saying that could be a very good example of this, because it does vary the higher your income is too. Yes, see, yes, perfect, perfect, perfect. So we have seen that 8 and 14 have been normalized. Okay, so everyone should have the model. Now what we're going to do is plot a histogram. And what we're going to do with this histogram is compare it to our earlier versions. We want to look at the skewness and the kurtosis as well. Okay, so what we're doing in this exercise is really understanding, we want to create a histogram of the skewness and the kurtosis so that we can investigate the skewness. Oh, someone already did it. Perfect. And we're going to compare it to the earlier histogram. Thank you, Maria, for putting the earlier one in there. I want you to really pay attention to, oh, is this the earlier or the latter? Okay, this is the latter. Let me put the earlier one in the chat so you can compare. This is one, and this is the latter. And we're gonna compare, oops. Oh, what happened here? Okay, so both histograms okay, so I just put it in the chat. I'm gonna bring over my Slack so we can see it better. Okay, the histogram on the right is the latter. It's the newer histogram that I just gave you the code for. What do you notice in the histograms that you see? What do you immediately notice? Less narrow. Yes. Skewness. Anyone notice anything with the with the outliers? Not as many outliers. Okay. So this one, you'd have to look at the scale, but what you can see is that the peak on these residuals, notice this one, the peak of the residuals is still higher than the normal distribution. It is also still narrower than the normal distribution. There are still some outliers on both sides. And the residuals are not symmetrical, meaning there are more outliers. Oh, wait, let me go back now. So what we can see is where before there were more outliers on the right side. So visually, we can't really say that the residuals improve, but this detail in the chart says differently. There are fewer outliers on the right, but there's still now more outliers on the left. So there are not many fewer outliers overall, but many are now peak below the peak, right? So a lot of them were above the peak before, but many are below the peak now. And this is what I mean by the peak. This little area right here. Oops. This is your peak. Okay. Um, so lower outliers are usually easier to explain because they're a product of known external factors versus higher outliers. What I mean by that is, let's say a customer or owner sells their house to a friend or relative, and that property may have sold less for a lower price, or a property is in bad condition, then it could be also sold at a lower price. These residuals are less skew and the tails are less fat. Okay. This is deduced from the skewness and the kurtosis metrics. And those are going back to our, let me come out of here. This is our skewness and our kurtosis. Let me go back to the chat too. Yes, I do. As you can see, I don't log into all of them. But anywho, we're going to go back to compare the two skewness and kurtosis of both models. So what you see here is, this is before and this is after. Okay, so what we're going to investigate now is, did heteroscedasticity improve? So we're going to look at a plot. Remember the before plot? Where we saw the violin and the scatter plot. We're going to basically create that plot again. Now I want you to tell me, did it improve? Just look at it and tell me, did it improve? Did the heteroscedasticity issue improve looking at the charts? Really? Just see. Okay. Make sure you also look at your scales, right? So let's go look at the scale. Did it improve? This is the before. Oh, maybe I'll just take a screenshot and do before and after. That might be easier. Okay. So yes, it improved. There is less variation. Remember the standard deviation on a $7 million home versus a $60,000 home? There's less variance here. Okay. What the residuals from the function of square footage has stabilized now, and now it supports the argument that you should be using the logarithmic scale because it's best for property prices. So now that we have that settled, oops, how do we interpret the units of the coefficient? So this is what I mean. This is your coefficient. How do we interpret the units here? Oops. I cannot draw today. How are we interpreting this? What happens when one unit increase or decrease happens? Is it a percentage change or decrease? Perfect. Okay, so basically what we're saying is if you had one additional unit decreases the log price of the property by 0.35. That's what we're saying. This also means it is a less than 30% reduction in price, which is calculated as this percentage change. Yes, perfect. Okay. So can someone tell me, there. So now that we know that one additional unit decreases the log price by 0.35, what does the coefficient tell us in this model? If you didn't see the units, I'm just gonna post this one here. All right, so now that we know an additional unit decreases the log price, so what happens with the square foot, that coefficient of square footage? Check out the coefficient, look at it in the I posted it in the slide. What does that 0.8687 mean? What happens? It's positive and it's less than 1. So since we took the logarithm of the square foot, this basically implies that there is linear or sublinear growth, and the price of the property goes up when the square footage goes up. There could also be diminishing returns. Perfect. Okay. So, give me 1 second. Okay, so what I also wanted to, oops. I'm checking in. All right, so Anna or Oscar, it is 11. I sent a message, but I don't know if you all seen it.
Hi, Tanika.
Hi.
Hello. So, it's okay if you take a little 2 minutes, but if you want to finish, we can like wrap it up.
Okay, cool, cool. All right, so let's go to outliers. How do you typically handle outliers? Let's talk about that really quick. Sometimes you're going to have very large residuals, but in general, how do you handle outliers? What are you doing to handle outliers? Z-score, you're checking your Z-score. Got a cowboy. Anything more than 3 sigmas, perfect. When you are analyzing residuals, our analysis had a lot of outliers. When we looked at that chart, there were some outliers here. So sometimes we have to figure out how we handle all of these outliers. When, as I said before, so anytime you are selling a property maybe lower than the expected price, you are going to have outliers. When you sell it higher than the expected price, you're going to have outliers. But this basically destabilizes our model. And what we need to do is remove any data points with very large residuals. But it could create bias. So high outliers that have higher residuals can't be determined before the model is created, which means they can't be removed in advance. We're getting into a catch-22. So what we should do is inspect our data beforehand using some of the processes that you all are mentioning in the chat. So you want to inspect your data, check for too small or too large values that seem out of place. And you really want to investigate why they're different. I said earlier, sometimes it takes me an hour of really data exploration. Once I'm looking at the data, running different queries to understand what's happening with the data, I'm running this different statistical functions to really understand where most of the data lies and where the minimum and maximum are, but where are a lot of my outliers. I use a lot of box plots as well. So you want to keep, once you do understand that, you want to keep that data set in mind. And then, you want to essentially print out you want to be able to see what those outliers are. So what we're going to do really quick is we want to understand what is the predicted values versus the actual sales price. So we're going to I'll put the code in the chat. And what you'll see in this model is, let me clear. The predicted sales price using the model that we have says the worst row shows $56,000. This is the worst row. The worst outlier is a house that sells for $56,000. It should have sold, should have sold for $56,000, but the sales price was $100. This same house was sold for almost $200,000, which tells me that $100 is definitely not the market price. I wish I could get a house for $100. I really do. But this is this is one of our worst records in this data set. So what you can also do is to investigate this is check all of the data. And you can see for this property, what were the multiple sales dates? And you'll see there was sold for almost 200,000 and then it was sold for 100. And that was just an 8-month difference. So this scatter plot that I'm going to put in the chat. So if you create a scatter plot of basically the chart of residuals versus the sales price for all your properties. So if you were to create a scatter plot of 100 versus 189,000, it would be a big gap difference. There would be a huge gap difference. But what we're going to do is create a scatter plot of all of the data. And what you'll notice is in the bottom left corner are the homes that were sold at a very much lower price. So there's some here. And then there's some here at the higher price. So some homes have been sold way lower than expected. And like I said, these could be the homes that have been friends, family, relatives. Sometimes you have to just do a transaction just to have it logged. So you might sell the home for $100, $50, whatever. So what I would want to do is remove any of those transactions that were probably less than $2,000 from the data set so that I would have more insight. And then I could run my model again. So basically, if I remove those outliers, I can quantify the effect of those outliers by taking them out, rerunning the regression model, and then see if any of the coefficients have changed. So here is the code, so you can see it, what I'm about to show you. Now let's look at how cleaning our data set will help out the coefficients. Okay. So a little less than 0.5% of the data set was moved. So a little less than half of the percentage of the model had outliers. And the unit's coefficient change, it was 0.35. If you remember earlier, about 35%. It was 0.35, but now it's 0.38. Even though that's not like a really big change, the standard error has changed 5 standard errors because the coefficient was 0.006. That's a significant change. It's now 4.66. It was 0.006. So this has actually improved our model. And now if you visualize this, what you'll see is those outliers are very much limited now. There are very limited outliers, whereas before there was a large number of those outliers. Now these smaller or larger properties that were resulting in big outliers, that's not happening as much. There isn't a big cluster of properties that are far away from zero. Whereas before you had the zero line, and then there were a bunch of properties further away from zero. So in this scatter plot, what you see is the center of the plot of residuals above may look like heteroscedasticity. But this effect can appear just because there are a lot of properties between 1,000 and 2,000 square feet. And it causes the scatter plot to like bulge or be fatter in the middle. And if you do the violin plots, it'll also show you that these doubts can be thrown out. So essentially in this case, you use linear regression to predict the property sales price in Milwaukee, but you also walk through various issues, outliers, heteroscedasticity, homeoscedasticity, the residuals. How do you update the residuals? How do you check for the standard deviation or the variance? When these assumptions of linear regression are basically violated, the normality of residuals and homeoscedasticity in the fitted model is destabilized, and then you cannot use that model. So as an example, we saw how a small number of outliers shifted a coefficient completely by several standard errors. So remember, the unit is now 4.66. It was 0.006. That is a complete shift. And what I want you to take from this case is recognizing heteroscedasticity in the residuals, why and how you can treat it, how you can transform the outcome variable to reduce your skewness, alleviating the heteroscedasticity, how you can treat outliers, how you conduct residual analysis. Okay. I think if we brought in some additional features, we could probably improve it. One of the features I think that would also play a big part is the neighborhood or the location. Let me see. All right. Thank you all. Let me know if you have any questions in the chat. I'm just going through it. Anna, I am done.
Thank you so much for the lesson, Tinika. It was awesome to have you with us, and we hope our fellows learned a lot. So I know we took a little bit of extra time, but we still have like 2 minutes, so you can like rest those 2 minutes, and we'll be back with more data science. Tinika, thank you so much. It was awesome to have you here.
You're welcome. Bye, everyone. Have a great day. Enjoy.
Thank you. Bye. So